optimization. Thank you very much to the jury. I'm really honored and proud of this award, and I'm very happy. Combinatorial optimization has been my field of investigation along all these years, and assignment problems and matching problems have been one of my subjects. So I decided to present a talk on the origins of combinatorial optimization and to highlight in a Euro conference the European roots of this discipline. So let's start with the birth of combinatorial optimization in the 50s. Why in the 50s? Because after the seminal works of the 40s, the simplex algorithm by young George Dantzig that you see here in an early picture, and the LP duality, officially by Alan Tucker, but for which, according to Dantzig, there was an anticipation. It was anticipated 1 year earlier by John von Neumann, or with his original name, Neumann Janos, from Hungary. So after these seminal works, the 50s saw the birth of combinatorial optimization through a series of results on particular problems and of general results that laid the foundations of this discipline. Probably the first extremely relevant scientific result was the famous 49-city instance of the traveling salesman problem, studied jointly by Dantzig, Delbert Fulkerson, and Samuel Johnson, who produced the first integer linear programming formulation of an important optimization problem, and the first development of cutting planes specific for this problem. Another seminal result came still in the first half of the decade from a young Harold Kuhn with the assignment problem. He developed the famous Hungarian algorithm that is known Hungarian because it directly derives from the work of two Hungarian mathematicians, Dennis Koenig and Jenő Egervary. That also has ancestors in the works of other European researchers, such as Frobenius and Jacobi, as we will see in more detail in a few minutes. Another famous result that almost all of us, or the majority of us, probably teach in the first course on operations research or computer science or graph theory, is the minimum spanning tree, for which we know two basic algorithms, the algorithm by Prim and the algorithm by Kruskal. However, these are the names by which these algorithms are famous, but these have been just rediscoveries, literally rediscoveries of identical algorithms developed by Czech mathematicians in the 20s that were published in Czech, on Czech journals, and at that time were unknown to the West, by Wojciech Jarnik, what we call the Prim algorithm, and by Oskar Borówka, what we call the Kruskal algorithm. Another basic problem is, of course, the maximum flow problem in networks and the famous max flow mean cut by Lester Ford and Delbert Fulkerson. But this result, too, is implied by a famous theorem by Karl Menger from Austria, known as the Menger's theorem, that relates the connectivity of a graph and the number of disjoint paths in the same graph, and that is in turn implied by early results by Koenig. And the other, probably most well-known field is that of shortest path, The two main algorithms emerged in those years were those by, again, Lester Ford and by Edsger Dijkstra. As you see, this has been the result of several years of activities on shortest path, to which also other mathematicians took part, but in practice, again, these algorithms can be as consequences of the Prim algorithm that is, again, from the works of Menger and Yarnik. And the 50s were, especially in the second half of the decade, also characterized by fundamental general methodologies that have been since then and are still nowadays fundamental tools, particularly for attacking NP-hard problems. The first result came early, was dynamic programming by Bellman, already in 1953, for try and solve in pseudo-polynomial time NP-hard problems. The second result is the cut-in-plane algorithm by Gomory in 1958 for the general integer linear program. And the decade was closed by the third fundamental tool, which is branch and bound method for the general integer linear program, developed by Land and Doig. I'm making just a brief stop here because, as Luke mentioned, there is a lack of ladies, and so far, indeed, we only encountered male mathematicians, and maybe not everybody is aware that the Land and Doig who invented the branch and bound algorithm are Aissa Land, British, and Alison Doig, Australian. Let's go back to the assignment problem, and let's start our tour of these results. The assignment problem is very famous and very simple. It can be defined in many equivalent ways. Probably the simplest one is to find given a square matrix, to find the permutation of the columns so that the sum of the values in which each row is associated with the permuted column is a maximum, or the classical binary problem with the two sets of n constants each, imposing that exactly one value selected in each row and column, or, and this is the one we will use for the next few minutes, the problem of finding a perfect matching of maximum value in a weighted bipartite graph. In spite of its simplicity, this problem has been one of the most intensively studied problems in the history of combinatorial optimization, and several hundreds of researchers, and the bibliography of assignment problem is well over 700 titles. Although it has older origins, it was defined in the modern way, in the way we all use when presenting it to the students, not by a mathematician, but by a psychologist. Robert Thorndike was the president of an American important division of the Psychological Association. You see here is a paper of 1950, exactly, the paper that opens the decades, where he defines the problem exactly in this way. We are given a set of n vacancies, n individuals to be used in filling them, and we want to give the jobs to the person so that the average success, which of course is equivalent to the maximum, the sum of the values will be a maximum. Besides this historical value, this paper is also interesting for a paragraph that it contains. Because once the psychologist had described this problem, he went to a mathematician. He understood it was a mathematical problem, and the mathematician pointed out that there was no problem because the number of permutations is finite. So the problem is solved. You simply compute all of them and take the maximum. And the poor psychologist observes that, okay, maybe this is a solution to the problem, but we were in 1950. Even 10 men and 10 jobs imply a number of permutations that no computer on earth can compute. So it is solved, but I cannot solve my problem. Indeed, it is quite curious that a psychologist anticipated something that mathematicians will recognize 15 years later with Jack Edmonds. Final observation, still nowadays, the fastest supercomputer on Earth, which is a Chinese parallel computer running at 93 petaflops. A petaflop is 10 power 15 floating point operations per second, can solve by brute force a 25 times 25 instance in less than 1 century. Kuhn became interested in this problem in 1953, when a pioneer in computing, Charles Tompkins, was trying to program a standard Western automatic computer that was at the time the fastest computer in the world to solve small size assignment problems. In that period, Kuhn was reading the first book ever published on graph theory by Dennis Koenig. I'm terrible in reading German, so I will say that it is Theory of Finite and Infinite Graphs, a book published in 1936. By the way, as Luke mentioned earlier, the second book on graph theory has been written by a gold medal, Claude Berger. And in that book, he found his augmenting path algorithm for the maximum cardinality matching on pure, non-weighted bipartite graphs. I mention this result because this is a fundamental step in the history of combinatorial optimization. But first, a few words on Dennis Koenig. He was a son of a famous mathematician, Hungarian mathematician, Gyula Koenig. He was of Jewish origin, but he was baptized as a Christian. He was a boy prodigy. He published his first paper at the age of 15. He studied with Minkowski in Göttingen. He got his doctorate. Then he returned to Budapest, where he became professor at the Polytechnic University. And his lecture, among others, were attended by people like Egervari, that we will encounter shortly, Erdős, Turan, Gallai. During World War II, he worked to help Jewish mathematicians. We stop here. This is the story of Dennis Koenig up to 1944. We will resume it later on. The matching theorem by Koenig is very simple. Given a bipartite graph, we want to find the matching of maximum cardinality. He introduces the concept of vertex cover. A vertex cover is a subset of the vertices such that every edge is incident with at least one vertex of this set. And the result is that the maximum cardinality of a matching is equal to the minimum cardinality of a vertex cover. And this is probably one of the first results that fully exploit the concept of duality. You see that there are various years here and also in the years where Frobenius studied the same problem. However, Frobenius proved a result that is, in a sense, equivalent to this result, but he proved it for matrices using combinatorial arguments. What is interesting in the proof by Koenig is the fact that he gave a constructive proof. So he gave an algorithm, a beautiful algorithm, that given any matching, possibly the empty matching, constructs a path that alternates non-matching and matching edges, such that when you then interchange them, you produce a new matching by cardinality increased by 1. And if it fails, then the theorem proves that this solution is the optimal solution. Maybe you will recognize in the idea behind this algorithm the fact that this is the ancestor of many modern algorithms, including the result by Ford and Ferguson. Let's resume the story of Koenig. We left him in 1944. Something on the history of Hungary in those years. From 1920 to 1944, Hungary was led by Miklos Horthy with a national conservative government. Today we will say center-right, probably. He kept the country in peace. He banned both the Hungarian Communist Party and the fascist Arrow Cross Party. But in the late 30s, he was forced to make an alliance with Germany and Italy against Russia. He was reluctant to contribute to the war effort, and in particular, he always refused the request to hand over Hungarian Jews to the Germans. In 1944, the year we are interested in, he even attempted to strike a secret deal with the Allies. The Germans learned that, and to control the country, they invaded it from air and land, removed Horthy from power, and installed a puppet government, and the Nazis started deporting Jews, and about 250,000 of them were deported to Auschwitz. You see here Koenig at that time. He was, as we said, of Jewish origin, but baptized as a Christian. So at a certain extent, he could consider himself to be safe. However, in October that year, fearing to be ordered to move to the ghetto, he committed suicide. Now we come to the second part of the Hungarian algorithm, that is one of the theorems by Egervary. We resume our story from the 50s with Kuhn reading the book of Koenig, and a footnote in that book pointed to a paper by Jenő Egervary, published in Hungarian, in an Hungarian journal, Mathematicae est Physicae Lapok, which means Journal of Mathematics and Physics. This is the 1931 issue of Mathematicae and Physicae Lapok, and this is an unreadable for me article by Egervary, the article mentioned by Koenig. Then Kuhn translated this algorithm using an Hungarian dictionary and published the translation as a research report that you see on the right of the George Washington University. By the way, it is still available. I asked it to the library of the George Washington University, and I got it in 2 days. And the translation is on combinatorial properties of matrices. It contains 2 theorems. One of them is most well known, is the one that produced the Hungarian algorithm. So I will say you few more on both theorems. First, again, some historical fact. Egervary was born in Debrecen. He took his doctorate under the supervision of Lipot Fejer, who has been the thesis advisors of mathematicians like John von Neumann, Paul Erdős, George Polya, and Paul Turan. So, good school. He had a wide scientific production, especially in what we call today applied mathematics. In 1931, he attended a lecture by Koenig, and he wrote that paper mentioned in the footnote in Koenig's books. In 1941, he became full professor at the Technical University of Budapest, and in 1955, head of the Department of Mathematics. And here again, we make a stop in our story, and we will resume it later on. To understand to fully catch the power of the first Egervary's theorem, remind the model of the mathematical model of the assignment problem and its dual. You see, its dual is elegant dual that we obtain by associating a dual variable to each of the 2 times n constants, and imposing to minimize the sum of the dual variables subject to the n-square constants, imposing that for each pair ij, the sum of the 2 corresponding dual variables is not less than the cost in the cost matrix. And strong duality theory, we know, ensures that the solution values of the 2 problems are the same. So the minimum of the dual is equal to the maximum of the primal. Now let's see the Eger-Varis theorem. I wrote it here using his words and his notation. And he defines a covering system, which is a set of rows and columns, of lines, then containing the ith row lambda I times, that is, with, he says, with the multiplicity lambda I, and the jth column with multiplicity mu j, and satisfy the fact that for any pair of variables, the sum of the 2 multipliers is not less than the corresponding cost. Of course, finding a feasible solution is very easy. We just select very large lambda and mu values. So the problem is find a covering system of minimum value. That is, find a covering system such that the sum of these 2 multiplicity indicator is as small as possible. So this problem is exactly the dual problem. And the first Eger-Varis theorem states the following, that given any square matrix of non-negative integers, the minimum sum of, we can call them dual multipliers, is exactly equal to the maximum solution of the primal problem. Let's assume the story, the biography of Jenő Eger-Vari to see this astonishing coincidence. In October 56, in Hungary, a student demonstration started a revolution against the Soviet-imposed policies. The revolution spread across Hungary, and in a few days, the government collapsed and was replaced by a democratic government. However, this had a very short life, as on November that year, a large Soviet force invaded Budapest and other parts of Hungary, especially with tanks and soldiers. There was a week of resistance by which 2,500 Hungarians and 700 Soviet troops were killed, and at the end of that period, in January the next year, the new Soviet-installed government had suppressed all public opposition and reinstalled the previous system. 200,000 Hungarians had to leave the country as refugees. You see here a picture of Eger-Vari at that time. He was then, as we saw earlier, head of the Department of Mathematics, but in the subsequent repression period, he was forced to retire under special pretexts that are mostly considered to come from a personal vendetta. And in 1958, fearing to be imprisoned, Eger-Vari committed suicide. For the third time, we go back to Kuhn. He then realized that the algorithm, the alternating algorithm by Koenig, and the result by Eger-Vari could be joined, could be combined, also because Eger-Vari proved his result again with an algorithm. That is, the proof of the Eger-Varis theorem is that given any feasible non-minimal sets of multipliers, there is a way to modify them so that they remain feasible and their sum decreases. So, and you can continue until you find the optimal solution to the dual problem. So combining the two methods, Kuhn reached finally an algorithm by which he could solve several 12 times 12 assignment problems by hand. And 8 years ago, he was a plenary speaker at Euro 14 in Lisbon, and he observed that this must have been one of the last times when pencil and paper could be the largest and fastest electronic computer in the world. He obviously christened, for obvious reason, this algorithm as the Hungarian algorithm. It was published on the Naval Research Logistics Quarterly. It has over 7,000 citations on Google Scholar, and it has been reprinted on the 50th anniversary of the publication. This is not the end of the story for what concerns the solution of the assignment problem and the Hungarian algorithm, because 7, 8 years ago, no, maybe 10 years ago, two French mathematicians discovered that they were studying the posthumous paper by one of the greatest mathematicians of all time, and discovered an unpublished manuscript written in 1851, that is 1 century early. And as you see, this mathematician was Jacobi. This paper is in Latin, De investigando ordine systematis equationum differentialium vulgarium cuiuscunque. That is about the research of the order of a system of arbitrary ordinary differential equations. What has this to do with the combinatorial optimization and with the assignment problem? The fact that after a couple of pages about this problem of finding an order of a system of differential equation, Jacobi finds that this problem can be transformed into another problem per se tractatus dignum, that is, that you deserves to be treated by itself. And this is the problem. Probably it is too small, but it said, suppose we have n times n quantities in schema quadrati, that is, in a square scheme, in such a way that there are n horizontal series and n vertical series, each of them of n terms. So the first question is, why didn't he write, suppose we have a matrix? Because the term matrix was not even known at that time. Let's continue. So he said, we have a matrix. And from all these quantities, we want to elect to find n transversales, he calls them in that way, that is in the horizontal and at the same time vertical rows in different positions. And immediately observe which can be done in 1 times 2 times n ways, the permutations. And from all these quantities, we want to find the one for which the sum of these n numbers is a maximum. So this is the definition of the assignment problem, without using the matrix, because the term matrix, this is maybe interesting to know, was coined in the same years by a British mathematician, James Sylvester. You see him here. And this time it is in English. At that time, they were studying determinants, not matrices. So he said, we have an arrangement of terms consisting of n lines and of m lines and n columns. And he says this will not in itself represent a determinant, but is, as it were, a matrix out of which we may form various systems of determinant by fixing a number p and selecting p lines and p columns. And he said we call them matrix. Why matrix? Because the structure generates determinants. So matrix is a term of the late 14th century, which means uterus, womb, and in Old French is matrice. And this is, again, the paper by Jacobi. This paper is terribly difficult to read. It doesn't give an algorithm. It gives a series of lemmata and theorems that finally produce an algorithm. And he felt the need of exemplifying it through a numerical example, a 7x7 numerical example, by which you can follow his method until to the optimal solution. And this method, it has been realized recently that it replicates exactly the patterns produced by the Hungarian algorithm. So this algorithm is the Hungarian algorithm. In the last 5 minutes, I will consider the second theorem by Egervari and its strange relationship with open shop, scheduling, satellite communication, and we are in 1931. There is a result that has been discovered and rediscovered several times, especially starting from the 70s. I mentioned the two main discoveries. One concerned telecommunication systems using satellites, in particular those who use the so-called time division multiple access technique. There are data buffered in ground stations. There is a satellite, and each station remits data to the satellite, who then remits it to another station. And on board the satellites, there are n transponders that connect the sending and the receiving stations. And we are given an n times n matrix, our usual cost matrix, in which each element, Cij, gives the time needed to transfer the data from station I to station J. And we want to find a transmission schedule so that all data are remitted in minimum total time. So in practice, we want to find permutation matrices, that is binary matrices with exactly 1, 1 per row and per column. A permutation matrix is, of course, a connection between the n sending station and n receiving stations. And for each permutation matrix, the transmission time, so that the sum of the permutations times the transmission times is at least the matrix to be transmitted, and the sum of the duration is a minimum. Another totally different problem, preemptive open shop scheduling. We are given n machines and n jobs. Each job must be processed on every machine in any order for prefixed number Cij of time units. As usual, each machine can process at most one job at a time, and no job can stay at the same time on two machines. We can interrupt the process, so the problem is preemptive open shop scheduling. If it is not preemptive, it is NP-hard, at any time and resume it later. And we want to find a schedule such that the completion time of the latest job is as small as possible. That is, we want to find permutation matrices that match a job and a machine and the processing times so that the sum of the processing times covers the matrix and the duration is a minimum. There are two algorithms for these two problems that have been studied in totally independent fields. In, say, our field, on Journal of ACM, Gonzalez and Sani presented a nice polynomial time algorithm. On IEEE, Transaction on Communications, Inukai, expert in telecommunications, presented an elegant polynomial time algorithm. These two algorithms are identical and are very simple and elegant. They are based on an observation that if we take the maximum row in a sum, this is obviously a lower bound on the optimal solution value. The same if we take the maximum sum in a column. And the maximum of the two is, of course, a lower bound for our solution. Then the algorithm works into two very simple steps. First step, add dummy values to the matrix so that all row and columns have the same sum equal to C star. And then iteratively subtract the permutation matrices at every iteration, taking as transmission or processing time the smallest positive cost corresponding to an element of the permutation matrix, until the matrix becomes 0. An observation, the matrix we obtain with all rows and sums summing up to the same value C star is the integer version of a well-known matrix, set of matrices which are known as doubly stochastic matrices. These are matrices with the real values, so that all row and column sums are equal to 1. And for doubly stochastic matrices, there is a famous result by Garrett Birkhoff that was published, this is quite curious, in Spanish in 1946, and somehow rediscovered some years later by John von Neumann, who proved it in a different way as a two-person game. This is the journal of the Universidad de Ciencias Exactas Puras y Aplicadas de la Universidad Nacional de Tucumán, Argentina. And Garrett Birkhoff published his result. You see here, we have in Spain here, so many of you can read it. Cada matriz que satisface condición satisface también the two sums equal to 1. Teorema, si una matriz satisface uno primero, entonces es una media aritmética de permutación. That is, every doubly stochastic matrix is a convex combination of permutation matrices. And the two algorithms we have just seen do exactly the same. They produce an integer version of a doubly stochastic matrix and put it to 0 through subtraction of permutation matrices. Which brings us to the second Egervari's theorem, which reads as follows. We are given a non-negative integer matrix C. Consider all possible permutation matrices. A system of permutation matrices which contains, in which the pkth matrix is contained lambda k times is called a diagonal coverage system for C. That is, it covers the given cost matrix if the sum of all permutation matrices times the multiplicities are at least equal to allCij's. So exactly what we are interested in. And the problem is find the diagonal system of minimum value. That is, the minimum time needed to process the jobs or to transmit the information. And the theorem states that the optimal solution is equal to the maximum between the maximum sum in a row and the maximum sum in a column. And what is even astonishing is the fact that the proof given by Egervari is this one. Obtain a measurand of the matrix, that is, a new matrix C star, such that all rows and columns sum up to C star. And iteratively subtract permutation matrices such that they are not all corresponding to 0 elements until the matrix becomes a 0 matrix. That is exactly the algorithm of the 70s, but in 1931. After his tragic death, and this coincidence with the death of Koenig, after the fall of the Berlin Wall, Egervari has been, rewarded with erecting a bust in the university gardens, with its death date, 1958, which brings us back to the 50 from which we started our tour. Thank you for your attention.
Thank you, Silvano, for taking us back in history and letting us remember how beautiful our discipline is and what interesting people were behind it. Thank you very much. I need to give you your medal.
I'm here for that.
You're here for that.